Is my screen visible?
Yes, sir.
Okay, thank you. So I think in our last class we discussed about small signal model. We started discussing about small signal model. If I remember correctly, then we started how to draw a small signal model for a MOS transistor. Am I right? Yes or no? Yes or no? Please respond, someone. Kartikeya, are you there? Hello? Am I audible?
Yes, I audible.
Okay. I think we have started discussing about small signal model for a MOS transistor, and we just drawn the MOSFET small signal model. Let me redraw it again. This is what your MOS transistor is going to be look like. This one, and it has certain terminals that you can represent it.
Sir, your screen is
It
not visible.
sorry,
Your screen is not visible.
screen is not visible.
Yes, sir.
Now,
Now it's fine.
okay, thank you. So this is what the MOS transistor that you see, and this is your drain terminal, and this is your source terminal. When you apply the gate voltage, then if, if that gate voltage is DC, and which create a channel, then you are going to have conduction in your transistor. And along with your DC source, if you apply an analog signal which is superimposed on the DC, then that analog signal getting amplified, and the transistor is supposed to be in saturation region of operation, right? So we had seen some of the things that we have discussed, that how to bias the transistor so that we're going to have the amplification. Okay, because when you take the DC biasing at the gate to source terminal, this is a gate and source terminal, you can call it as VGS. If there is no DC voltage applied here, if you apply directly an analog signal without any DC, then this analog signal cannot create an inversion layer. It means transistor itself is in inactive position, which cannot you know, amplify your input signal that you are trying to apply here. You can call it as which is VI. Right? Along with this analog signal, you have to apply some DC, which create an inversion layer, and transistor is live, and there is an amplification in your input voltage that you are applying. Right? So considering that factor, we want to do sort of DC analysis as well as the small signal analysis. For a small signal analysis, we require small signal model for a MOS transistor. So we are going to drawing a small signal model for a MOS transistor. Small signal model. So how it is going to look like when you have a gate terminal, this is referred to be a gate, and the analog signal that you're going to apply here is referred to be positive, negative, and which is VGS. And your source terminal is there. It may be connected to ground or not, depends on the configuration that you're going to have. As you apply the gate voltage along with your DC biasing in small signal model, when you apply a DC voltage here, this DC voltage for analog small signal model, we treat it as ground. So we are not going to drawing that DC signal over here because we are doing the small signal model and we are not representing it in our small signal model. So what is going to happen is that here we have the current, and we'll get the transconductance Gm times VGS, and this Gm times VGS based on this input that you are going to apply along with your DC biasing conditions. And this is referred to your drain terminal, source terminal. Someone is unmuted their mic. Please mute yourself, all of you. CR, please inform them no one's supposed to be unmute their mic. Mr. Ajay Kumar,
Sure.
this is what I keep on reminding in the regular classes that student they are present but not physically. Please do not repeat these kind of activities while the class is going on. It disturbs a lot. So this is referred to be your small signal model for a MOS transistor. And when you have a channel length modulation factor, then it causes to be resistance. We already calculated that value or not. Channel length modulation factor, which is going to be added in your current, which is half mu n COX W by L VGS minus VTH whole square into 1 plus lambda times VDS. As VDS value changes, then you'll go into variation. You can see. Now we will talk about this R naught value that is referred to be transistor resistance, or you can call it a channel length modulation resistance, which is given as 1 over lambda times ID. Okay. If lambda value is small, and then you're going to have the larger value of R naught. Okay, if lambda value is higher, then you'll get smaller value of R naught. So depends on this value of these two terms, and then you're going to have R naught value, and you want to account the channel length modulation factor here, then you just add your resistance called as R naught. In some of the textbooks, people can write it as RD also, drain resistance, because at the drain terminal. Okay, so this is referred to be your kind of small signal model for a MOS transistor, right? And this sometimes you can write it as, instead of this R naught, you can also write it as current source, which is alpha times VDS, because it depends on the value of VDS. Because as VDS value higher, then you have a channel length modulation factor, and which causes to be small increment in your current, and which results into the RD value, right? And along with this, if you are interested to add the body biasing effect into your small signal model, then it is going to be added here. So let me redraw with other color. When the body biasing, when you have a source terminal, and then let me treat it as my body terminal, which is body B, right? So when there is a biasing voltage between body and source, consider this is body positive and source is negative. So here you have a VBS, body to source voltage, right? Then you're going to have one more terminal that is getting added here, which is referred to be the gain, sorry, transconductance, which is because of the body biasing. GMB is a transconductance which is because of the body biasing, and which is caused because of your VBS value that you are applying. Okay, this VBS is there in your transistor, means body biasing is there. Then you're going to consider this term into your small signal model if there is any body biasing in your amplifier circuit. If there is no body biasing, then you can discard this part, and this part you can draw simply this model if you are assuming that there is a channel length modulation factor in it. If there is no channel length modulation factor, then what you can essentially consider only the red color. Now picture that you can see here is this one, that you can draw it for your small signal model of a MOS transistor. Okay, so with this background, let's try to build an amplifier. We consider, we basically start with common source amplifier, and then we'll see how the analysis is going to be for a common source amplifier. You can call it as a single stage amplifiers also, right? So this analysis also referred to be a single stage amplifiers. So single stage amplifiers. And the first category that I can consider here is that common source amplifier with a load of resistive load. So when we were talking about the inverter circuit, inverter design, then we have started about the inverter with resistive load, and then depletion type, enhancement type load, and then CMOS load. So basically we have started with resistor because it gives you a kind of analysis to analyze the given circuitry. So we'll start the single stage amplifier with common source configuration, and the load element is your resistive load. And the general structure of your common source amplifier is depicted over here. So we have a single MOS transistor called as NMOS transistor, and whose gate terminal is connected to a small signal. You can call it as a microphone, and along with that there is a DC biasing on it, right? And now this source terminal is, so this is your source and this is your gate terminal, this is Vi, and this is the gate voltage that you are applying for biasing of your transistor. And here we'll tap the output called as V out. Okay. And there is a supply line which is connected through a resistor called as load resistor. You can refer it as RD resistor or RL resistor. Depends on your way of convention, you can write it. So this is the drain terminal of a MOS transistor. So if you notice carefully here, the output voltage which is equivalent of VDS, right? Drain to source voltage is equivalent of V0. Okay, which normally depicted over here, which is referred to be VDS. So here VDS is which is equivalent of V0. Okay, and there is a current in your transistor which is referred to be ID, is depicted over there. Now if you try to do first DC analysis and then we'll go for an small signal analysis for this common source amplifier with resistive load. So here you can write it as resistive load. Okay, because we are using resistor as a load element and then we are trying to analyze it. Now if you recollect from the inverter characteristics, the only difference you can find here is that here we have a small signal Vi which is connected here. There is the only difference, and rest of the things is same as that of your inverter circuitry. Right? We call it as common source because your source terminal which is connected, this one, the source terminal which is common for the input side and which is common for your output side. So you can call it as common source amplifier, and then load element is a resistor. So you can call it as common source resistive load amplifier. Okay. Now if I do DC analysis for this common source resistive load element, let's go for DC analysis or large signal analysis. Okay. Then what you can see here is that the VG, when you are talking about DC analysis, then small signal considered to be smaller in magnitude, you can neglect them. Then eventually you can consider the gate to source voltage, that is VGS, which is equivalent of VG. So as we are writing this drain voltage, which is supply voltage that we are talking about, which is referred to be a VDD, you can consider VG value as VGG also for a conventional way of representation. That's it, nothing else. You can consider any other value or V0 or V1, doesn't changes, but here we are representing it as VGG because the drain supply voltage that we are calling as VDD, you can call the DC bias voltage that you are applying to the gate to source terminal is VGG. Okay, for DC analysis, what you are trying to do is Vi, the analog signal is 0. You are not applying any analog signal here. Okay, and VGS, gate to source voltage, which is equivalent of the VGG value. Okay, and if you write the current ID expression, ID, which is equivalent of what can be written as VDD minus VDS by RD. This is what you can write it. Basically, you just take a KVL from VDD to the output node and write the KVL loop here. Then you will get the VDS value, or you can call it as load voltage across a load resistor RL, and from there you can easily calculate the value of ID, which is depicted here. Now what you can do is you can plot the graph for ID variation with respect to VDS. Then it is going to be something like this. Now if I draw a plot here, x-axis is depicting VDS and y-axis is depicting ID. Basically it is output plot or output characteristics of a transistor. We are drawing it is for a transistor, and we are well aware that as your gate to source voltage is smaller, then you have a smaller current. As the gate to source voltage increases, then there is an increment in your current. So let me depict with different colors here. This is how you can see this. This is for VGS1, and you can consider this is VGS3. You can consider this is 4, VGS4, as you are increasing the VGS value. Now from this DC analysis, what you can notice here is that ID, which is equivalent of VDD minus VDS by RD, right? At VDS value is equal to 0, now you can consider VDS which is equal to 0 volts. Then what is your ID current? Okay, means drain to source voltage is equivalent to 0. Then you have a current. Now you subtract this VDS value which is equal to 0, then which is VDD by RD. So it is referred to be a VDD by RD resistance. Okay, because VDS is equals to 0, and that point of time you have a maximum current in your transistor, and that current is depicted somewhere here. This is the maximum current that you're going to get, which is VDD by RD. As your VDS value is going to be increases from 0 to higher value, then this numerator term which is there in your current expression is going to be drops slowly as VDS value increases, and then you will going to have lesser current in your transistor. So as VDS value is becoming, now here VDS is equivalent to VDD, then numerator term going to be 0, and finally you're going to have the current which is equal to 0, and which is at VDS is equal to VDD. So when your VDS is equal to VDD, then you have the current called as 0 current. Okay. When VDS is equal to 0, then you have a maximum current. When VDS is becoming VDD, then you have a 0 current in your transistor. Now you join these 2 points, then you'll get a line called as DC load line. So in your EDC class, you might have seen that this line is referred to be a DC load line point. Okay. And one thing you can also notice from this green color lines is that, so these are referred to be some of the points which indicates that the variation of different region of operation of your mass transistor. So up to this region you can call it as saturation, sorry, this is for your linear, and above this you can have the saturation point. Okay. Now what we are going to do here is that as you vary the values, right, which is referred to be VDD, that is VGS value, as you vary the VGS value, then you're going to have variation in the current. So as VGS value is equal to 0, means VGG value, VGS nothing but here VGG, which is equal to 0, then you have a 0 current here. As it is increases, then you are moving in this direction, and then you're going to have higher and higher current. And there is a demarcation point here where you are moving from saturation region to the linear region of operation of your MOS transistor. Okay. What it indicating is that you are trying to biasing your transistor with the help of a VGG voltage. Then you have to fix it to certain value, and that value is supposed to be at a quiescent point. It's supposed to be somewhere here. You can say that this one, it is somewhere here. This is referred to be quiescent point. You can call it as RQ point. Okay. So as you fix this value, then there is no variation in your biasing condition of your transistor. So this is IDQ and this is VDQ. So you have to apply certain voltage here at a gate to source, and then you need to fix this biasing condition so that you will get perfect amplification. Okay. Now if you draw the VTC plot of a transistor, consider this one as your VGG value is increasing from 0 volts to higher voltage. Okay, and this is your V naught. So we are trying to draw V input by V output characteristics. As your input is equal to smaller in magnitude for a transistor, means DC voltage we are talking about here. As you have smaller DC value, then what happens your transistor is off until it reaches to the point called as threshold voltage. So when it is less than threshold voltage, then you have output voltage is equal to maximum. Up to this point, you're going to have the maximum output voltage, and further increment in your VG, then you will have a variation in your input output plots. As it is going beyond VT value, then it start drops, something like this, right? Now you can see this plot where there is a steep transition of your output to input is going to occur, and from this point onwards your transistor is reaching into this linear region of operation. Okay, so this is a region where your transistor is cut off basically, and this is linear, and this is a two region in between cut off and then linear. operate under saturation region of operation. So you have to operate your mass transistor into saturation region of operation so that there is an amplification takes place. Now, as there is an input variation, small signal, so this is referred to be a DC voltage, right? And added with DC voltage, there is a small signal which you are going to apply here, and which is referred to be smaller in amplitude. Let me draw the small signal here, which is exactly center of the this one here. If you try to draw a small signal model, it's small signal here, which is depicting something like this, very small in magnitude. But correspondingly, you can see that there is a variation in your current, which is referred to be very huge. This one. So this is a point where you can see that this negative peak, and this is referred to be a positive peak, this one. So when you talk about this is the center point, then you're going to have this kind of amplification over here, which is referred to be something like this. Okay, so here the signal is smaller in magnitude because it is operating under saturation region of operation, and there is a maximum current that you can see, which is going to be getting amplified, and which is because the transistor is operating in the saturation region of operation. So sorry, here the we are talking about only the voltages. As you are increasing the voltages, then corresponding output voltage variation you can see as a maximum in amplitude, right? So during this fixing the value of your VGG, what you need to do is you need to fix a Q point, and that should be greater than the threshold voltage of the transistor. So if it is less than threshold voltage, then there is no amplification in our transistor, because transistor itself is off, because it is under cutoff region of operation. Where it is above VT, then it going in saturation, operate the transistor in saturation, then there is a maximum amplification for your transistor. Okay, so what you require basically is biasings in such a way that, let's say here it is 0 voltage, that is referred to be your biasing, which this is V G voltage is exactly at 0, and then you are applying analog signal here, and you have a threshold voltage of the transistor, let's say it is the here. So below this threshold voltage, the analog signal that you apply here is not recognized by the transistor. When it is exactly at this threshold voltage, what is going to happen is that when it is exactly threshold voltage, transistor recognize only the positive peak. This portion is recognized, but not the negative peak, because it is exactly VT, and negative is going below the VT, so it cannot recognize. So what you have to do is, it is always well above the VT value, and fix the value of VG here. So this is your VGG or VG value. It is well above the VT value, so that maximum amplification can takes place in your circuitry. So here, if it is going this way, now the transistor recognize both positive peak and negative peak of your small signal, and which is getting amplified. Now coming back to this output and output plot of your transistor, this VD value, this point, then it should not be so close to this VDD level and so close to this level, because when you apply this signal here, this should not get clipped positive portion of your signal or negative portion of the signal, because as it is going in this direction, let's say here, if it is going in this way, then this peak is getting clipped out, let's say this one. So now we are fixing the value called as this one, that is your VG value, that is gate biasing voltage that you are talking about here, means you are fixing at this point, let's say. Then your analog signal is something like this, let's say. After this point, the positive peak getting clipped because it is not recognized by the transistor. Okay, so it should not be very close to this VDD level, and it is not very less value close to 0 level, because there is a possibility of clipping of positive peak or negative peak of your analog signal once it is getting amplified. So to avoid that, what we'll try to do is we fix at the center of this region, so that none of the peaks, positive or negative, should be clipped out, should not be clipped out. Okay. So during this process, what you need to focus on is that VDS value should be greater than or equal to VGS minus VT, which ensures that the transistor is under saturation region of operations. Okay. Now, if we do the AC analysis for this, for a resistive load, going back to the resistive load in common source amplifier, this is what depicted over there. Let me redraw it again. Resistor referred to be RD, the transistor that we are applying here, and then this is the point where we are tapping in called as V out. This is VDD, right? And then there is a current in the device called as ID, and this is your VDS, and VDS is equivalent of V out. And this is your VGS. When your small signal is 0, then VGS is equal to VGG. Now, if we do the AC analysis, small signal analysis, you can write it as small signal analysis. So during the small signal analysis, what you have to do is you have to take certain rules that DC sources must be connected to ground. Okay, all your DC sources are connected to ground. So whenever you have a VGG and VDD is equivalent to 0 and VGG is equivalent to 0, and then you have to draw a small signal model for it. So this configuration is going to be redrawn here. Let me redraw it here. This small signal ground, this is connected to ground, and this is connected to ground. This is RD, and this is your V0. This is what you can see while doing this small signal model, right? And you are well aware regarding this small signal equivalent model for your MOS transistor. Okay, so let me write the small signal model here. So this is your gate terminal, drain terminal, and source terminal of your MOS transistor. So first draw the small signal model here. This is the gate terminal that you have, and this is the source terminal which is connected to ground. Let me represent with source. This is source and negative. This is positive, and here it is VGS, gate to source voltage, and which is connected to here V input, which is given over there, which is VI. And here what you can see is that GM times VGS, and this is your drain terminal that you're going to have. Okay. So now you see this 3 terminal of your transistor, source is connected, gate is connected, drain side along with this, and if there is channel length modulation factor, let's account that factor also, which is R0. And this is for your transistor, and then extra component which is RD is connected there. So you just write the RD here, because this RD which is connected from drain terminal to the ground, right? So AC ground signal. So it is connected to AC ground. So drain to AC ground. So this is our DC drain terminal, and from there you have to connect RD to AC ground, and here which is RD. And this is a point where you can call it as V out, right? So this is the small signal equivalent model for a resistive load inverter by considering all DC sources are equivalent to 0, right? For a small signal model, when you are trying to designing an amplifier, then there are 3 major parameters that we need to remember all the time. And those 3 parameters are normally the gain of an circuitry, and input resistance of a circuitry, and output resistance of a circuitry. So these 3 parameters are always need to be analyzed to judge the amplifier performance. Okay, the first parameter is your gain of amplifier, which is V out by V input, and input resistance of an amplifier and output resistance of an amplifier. Okay, let's calculate the value of your gain first. Okay, so how do we calculate the gain? Now, when the current is coming in this direction, let's say this is the current which is coming, and due to which here you have the GM and VGS, and these 2 resistors are connected in parallel. Now you can consider that these 2 resistance equivalent, which is R0 parallel with RD, which is referred to be a single resistance, because this R0 parallel RD is the equivalent resistance per parallel resistance of these 2, R0 and RD. Okay, so V0, which is referred to be the voltage across these 2 resistors, are equivalent resistor of R0 parallel RD, right? So what we can write it here, V out or V0, then it does V0, which is equivalent of R0 parallel with RD, right? And here the output voltage that we are trying to draw is always, when we talk about output voltage here, this output voltage is always 180-degree phase shift of the input voltage that you apply here, right? So here it is from positive to negative, but here it is from negative to positive. So the output voltage is always 180-degree phase apart. So because of the 180-degree phase apart, you just add the negative sign here. Okay? And the resistance multiplied with your current, the current here is GM times VGS. And here VGS, which is equal to V input. So V naught, which is equal to minus GM times V in times R naught parallel with RD. Now if you take V naught by V input, which is referred to be a gain of this circuitry, is minus GM times R naught parallel with RD resistor that you are connected. So this is the gain of an amplifier where the resistive load connected for a common source. So this is a common source resistive load amplifier, single stage amplifier gain. So minus GM times R naught parallel with RD. If RD value is neglected, there is no channel length modulation factor, then what you can write it as minus GM times RD resistor. So RD here is a load resistor that you have connected. Okay. Now, if we are interested to analyze the what you call input resistance of this stage, so now where you try to calculate the input resistance. Input resistance is supposed to be calculated at this point. So now here this is your RI point to be calculated, input resistance. Okay. So when you try to calculate the input resistance and now you look at this AC model carefully, so here you are trying to calculate the RI value, input resistance, then here VGS, which is equivalent of VI and which is pretty small in magnitude. And now when you talk about this VGS where VGS and it is open circuited here, means gate and source terminals are open circuited, and then now you're talking about current here, current is equivalent to 0 because gate to source terminals are open circuited, there is no current flowing through gate to source terminal over there. So what you can write it is here is R input, which is referred to be I input by VGS. So here current is referred to be 0, and which makes input resistance of your circuitry is infinite. Okay, infinite input resistance. So for an amplifier, you require input resistance should be as high as possible, close to infinite, and output resistance must be as low as possible to drive larger loads. Right? So now if you calculate the output resistance, so we calculated the gain, input resistance, now we try to calculate output resistance. Then if you draw the small signal model again here, this is a small signal that you are applying. This is VGS, source terminal, GM times VGS, this is R naught, RD, and this is your V out. So output resistance is calculated. Now we are trying to estimate the value of R out. So when you try to calculate the output resistance, the condition here is that input signal V input must be 0. Okay. So what you have to do, this signal made to be 0 so that VGS is equal to 0, and then GM times VGS is also going to be 0. And here externally you connect a source, right? Here from these 2 points, which is referred to by Vx, positive and negative, and because of that there is a current in your circuitry called as Ix. As you apply this Vx voltage externally, which because of the resistance presented over in this network, which causes to be current here, now you can calculate the R out, which is referred to be Vx by Ix. Okay. Now what is the resistance present here? The resistance which is equivalent of this. Okay. So what you can write it here is that RD parallel with R naught, okay, into Ix divided by Ix. So this two gets cancelled out, then you will end up with R naught value is RD parallel with R naught. This is your output resistance of your amplifier. Okay. So we try to estimate it the three parameters: gain, input resistance, and an output resistance of an amplifier. So in gain of amplifier, which is given as minus GM times this one, R naught parallel RD. Input resistance is given as infinite. Output resistance is RD parallel with R naught. So these are the some of the parameter by which you can analyze the performance of your amplifier. So if you know to RD value and then R naught value, you can easily calculate what is actually value of R naught. And similarly, when you are aware of the GM value and then R naught value and RD, then you can easily calculate your gain of an amplifier, which is GM times R naught parallel with RD. And similarly, input resistance definitely is going to be infinite. So with this parameter, you can analyze it whether it is okay for amplification of your circuitry or not. Okay. Now with these parameters, first let's analyze our common source amplifier, and then we'll move on further to checking the alternative way of doing it. Okay. Now let's take an amplifier. It's common source amplifier only. So let me write it something like this. Let me draw a common source amplifier, which is RD resistance. Now here we have a microphone which gives our signal, or else you can consider small signal Vi. So this is your Vi, and biasing voltage that you try to apply here, connected to ground, and similarly here source is connected to ground, source, gate, drain. This is the VDD, and this is your Vout. Okay, and here what are the parameters that we are aware and not aware is that, so consider that gain of this amplifier, which is aware that AV is minus GM times RD, provided that if lambda is equal to 0, if lambda is 0, then RD value is going to be 0, and you will end up with the value of gain of an amplifier, which is equal to minus GM times RD. Now by looking this expression, what you can write it here is that minus GM times, instead of depicting in a formula, you can make it in the form of a statement for a gain of an amplifier is that, let's go back and revisit this one. So here what you can see is minus GM times, minus is because of this 180-degree phase shift, and R naught parallel with RD. This is what you can notice from your small signal model. This is what. So this configuration gives us something intuitive, that what you can comment is that gain of an amplifier with resistive load, which is equivalent of minus GM times the total resistance presented at the drain terminal. So at this terminal, the total resistance presented here multiplied with minus GM will give you the gain of an amplifier. That is what we are trying to write it here. What we'll write it here is minus GM times the total resistance from drain to AC signal ground. So the total resistance which is available from drain terminal to AC ground signal, that resistance need to be connected, and which is gives you the gain of an amplifier. Considering that factor, if we try to modify this existing circuitry, then what is the gain of an amplifier that we want to analyze it? Let's take a small modified version of this circuitry. Let's say we have same common source amplifier, VI and DC biasing, this one, and here which is V naught RD resistor that we have, which is VDD. Now with this VDD again, what we'll try to do is we added a resistor called as R1. Let's added a resistor called as R1. Now then what is the gain of an amplifier? Now will you able to analyze the gain of an amplifier? From this statement, what you can write it is that minus GM, that is a GM of an transistor, gain of transistor, into the total resistance tied from drain terminal to AC signal ground. When you do AC analysis, this is connected to 0, this is connected to 0. So these two resistors are going to be in parallel. And what you can write it here is that, which is R D parallel with, sorry, R naught parallel with RD if there is a channel length modulation factor, and parallel with R1 resistor. This is what the gain of amplifier that you can see. This factor is common, and now one more resistor is added, which is referred to be R1, is this one. So this R1 resistor is added, which is in parallel with the existing resistor or not parallel with RD. Now if there is one more resistor is getting added to that, which is this one. Let's say here you added a one more resistor called as R2. Now this resistor is also going in parallel with this existing resistors. Then the gain of an amplifier, which can be written as AV, is minus GM times, okay, R naught parallel with RD is common, and then R1 resistor is added here. Okay. Along with that, in parallel with that, there is a one more resistor which is added, which is R2. This is what the total gain of an amplifier that you can notice. Right? So if you neglect the value of R0 here, then RD parallel with R1 parallel with R2. Otherwise, all four resistors which is available to you are going in parallel, and then now if you are able to calculate the resistance of these all four resistors, then you multiply with GM and the negative sign, then you will get the gain of an amplifier for a resistive load kind of circuit. Okay, there's a kind of analysis if some of the component is getting added along with the existing circuitries. Okay, and let's take a simple example with the numerical, and then let's analyze this configuration. Okay, so quickly let me draw this. This is VDD and this is RD resistor. And this is your V0. Okay, so the parameter which is given here is that this is your Vi. Okay, this is a small signal, and RD value, this is drain resistance, is given as 3 kilo ohm, and W by L of your transistor, which is given as 10, and mu n COX, that is transistor parameters, mu n COX, which is given as 100 microampere per volt square. And threshold voltage of the transistor, which is referred to be your 0.5 volts, and threshold voltage of the transistor is 0.5 volts, and the channel length modulation factor is 0, and your V0 value, this is referred to be V0 value or VGG, you can call it as. Now this is VGG is equivalent of 1.2 volts, that is DC biasing voltage, and the supply voltage VDD is given as 2 volts. Okay, so you can analyze the performance of this circuitry. So to analyze the performance of the circuitry, what you have to do is first calculate the biasing points of your transistor, because when you apply the gain formula, that gain formula is valid when the transistor is under saturation region of operation. So first you have to ensure the transistor in saturation, then apply the gain formula. That is going to be valid. Or else first you assume that the transistor in you know